Hi, my name's James Tormbadore, and today I'm going to be talking about my senior design project, which I worked on during the 2017-2018 academic year at UC Santa Cruz. I worked alongside David Kooi, Donald Avansino, and Keifer Selmon, and our project was sponsored by Topcon, which is a positioning systems laboratory that comes up with solutions mainly geared towards the fields of agriculture, medicine, and construction. And so Topcon came to us and they said, all right, we want to look at how we could automate some of the functionalities and tasks that's required of a bulldozer at an everyday construction site. And specifically, we looked at how a bulldozer is needed to move piles of debris from point to point at a construction site and how we could better automate that task. So to do this, we primarily relied on computer vision, and we used computer vision for essentially all of our sensory input, for being able to recognize piles of debris as targets, being able to align with piles and approach them. And once we've approached them, being able to feel spatially how the pile is, and how it looks, and making sure that we're able to penetrate the pile effectively so that when we are trying to scoop up some of the material, we're getting a full bucket every single time, and being able to verify that our bucket's full every single time. And so the rest of this presentation will be talking about those individual parts and how we executed them. So to get started, let's talk about what we worked on. We worked on this model replica of a bulldozer called the Housecat Mark II, which has its main sensory input coming from these sets of cameras. So we use this 2D camera to essentially do our target finding. And we use these stereo cameras to be able to get a spatial representation of our environment when we're close to a target. You can kind of think of these stereo cameras as eyes. These stereo cameras work as eyes because you're able to get two images, and because you have a distance between your two eyes, you're actually able to get a depth understanding of how far away something is from you. It's really hard to tell how far away something is when you just cover one eye. And so this is the same exact idea that applies here. We use these stereo cameras to generate a 3D representation of our world. The Housecat also comes with an onboard Wi-Fi router because we do all of our processing on an offboard CPU tower. And we also developed all of our algorithms on top of ROS. This is the MoveX M48, which is actually a larger scale remote controlled bulldozer for commercial applications. It's about the size of a small SUV, and it's all remote controlled, but with Topcon we actually modified it and we're able to put all of the functionalities which we developed, which we'll be presenting today, onto the MoveX M48, and we actually were able to test some of the functionalities in a real-world construction site, not just a lab setting, and validate some of our results. So the first thing we need to talk about is how we were able to identify stockpiles and approach them and align ourselves with these stockpiles. So to do this, we actually trained a neural network to be able to recognize stockpiles, and we did this by taking pictures of stockpiles and actually classifying them, and then training a network on top of that. And so what our algorithm does is first it grayscales the image, and then we're able to do a prediction on top of that grayscaled image and be able to find our target, which would be our stockpile that we're trying to approach, and might be the target that we're trying to move from point to point. To better verify that we're actually looking at the right target, we've also trained other networks that are able to determine texture of a material. And so to do this, we take that boxed target from our initial network and we pass it through another network that determines the texture by taking that boxed image, slicing it up into individual smaller boxes of images, which is what you see here. And you can see that we've sliced these up into little boxes, and we have predictions based on the texture that we see. And so the texture analyzer that is being applied here is for wood chips, which is the type of material that we're looking at here. And so you can see where the little box that would be cut out, it has a much higher confidence, closer to 1, because it sees the material that it's looking for. And the types of materials that we're able to detect currently are things like wood chips, gravel, and sand, among some few other things. And so to give you a demonstration, or excuse me. So once we have this texture analysis, we're actually able to find the center of the pile, because we can kind of determine, okay, where's the part of the box where the mass is the most consistent, and so we can find where the texture is the most consistent throughout the entire boxed image, and from there we can kind of determine a center of mass on which we should align ourselves when we're driving towards a pile. But to show this in a demo application, we have this video where the house cat is going to be looking for a target, specifically a wood chip target. So it's able to determine that rock pile is a stockpile of material, but it's able to determine that that's a pile of rocks rather than wood chips or a pile of gravel. And so once it finds the wood chips, which is the type of material that it's looking for, it's able to identify that and then align itself to that pile towards the center of mass. So once we get close to our target, the next thing to do is our stereo camera process. And again, our stereo camera process begins with taking images from those two cameras that I showed in the very beginning. And like eyes, we're able to essentially get a difference. We know our physical difference from the camera. And so we have this spatial distance where we can look at the two images, and using trigonometry, we're able to determine how the two images relate and how the depth of the image, how the depth of the space in front of us is. And so we're able to determine or generate this disparity map, which you see here, which is the colored image. And from there you can filter that image to get rid of some of the noise or some of the things that we're not trying to look at. And from there, we're actually able to take those depth points and generate a 3D representation of the pile that's in front of us, which you can see in that last frame to the right. And from that, we're actually able to determine an approach trajectory on a given pile, because there are certain ways that you want to be entering into a pile when trying to dig the material. So to do that, to find that optimal approach calculation for how to dig into a pile, the first thing we do is that we take that 3D representation of our pile and we find the peak straight ahead of the robot. And from that we create a reference plane with its origin at that peak we found. And then using a KD decision tree, we can essentially sweep that plane from pi to 2 pi across the pile in front of us, and this is all done during that 3D, with that 3D model we've generated. We're able to find where the intersection of greatest area is, which is the trajectory on which we should be digging, because we want to be penetrating into that intersection of maximum area so that we're not splitting the pile into two pieces and we're keeping the pile more nice and neat. So what we can do is we can essentially transform our robot and align ourselves with that intersection of maximum area. And so here's an example video of that in real time. So it takes the disparity map, and then we generate our 3D representation here, and those balls are actually that path that it's generated, that intersection of greatest area in which we're trying to align our bulldozer with. And so the bulldozer is going to follow that transformation, and it's going to double check here and regenerate the entire 3D point cloud. And then since it's in that intersection of greatest area, it's going to go for a dig and be able to get a full bucket, and also keep the pile nice and tight and neat for efficiency. Because if you go through the middle, you might cut the pile in half, creating two different piles, or spread the material thin, which is very hard to deal with. So then once we've filled our bucket, or we've attempted to do a dig, the next thing we have to do is verify that our dig was successful. And so to do that, we're actually able to lift the bucket up, just as you saw at the end of the very last demo video, and use our center camera to look and take a picture of our bucket and reapply that texture analysis network to determine, do we have the right material in our bucket and do we have enough of it? So the way we do that is we lift the bucket, we look at it with the center camera, and we split that picture up into smaller boxes, and again look at the texture. And if the texture is above the required threshold, the red number is not printed, and we're able to determine that, okay, there's material there. And so from that we can say that we have enough material if enough of that bucket is filled, if there's enough positives And so this, in an example here, so the robot decided that it wanted to dig on this pile because it thought it was had a good trajectory. But one of our teammates, Keifer, kept it from going, and so it's going to try and look at its bucket. It does that little shift to kind of level any material in there, and you'll see that this picture that comes up has a bunch of red negative values, and that's because there's no material found in the bucket. So the robot knows that, and it's pointless for it to try and find its waypoint to drop off material because there is no material. So what it's going to do is it's going to realign itself and try to dig the pile again. So here it made a mistake where it thought it was close enough, and so it's going to level that material and check again. But it didn't get enough material, and you can see that because there are some values that made it through, but not enough. And so the robot says, okay, this isn't worth my time, so I'm going to try and get more material and try again. So the robot's going to get a lot closer this time. Make sure that it's getting the right trajectory, and then try and scoop the material again. So here it's going to level out the material again. We're going to look at it for a picture, and this is above roughly 60-70%, which is the requirement that we have for how full the bucket needs to be. And so it's decided that the bucket is full enough. This is a worthwhile amount of material to traverse to a dump site for. And so we've marked our dump site by a cone, and the robot will now traverse to this cone. Again, using a neural network to track it in real time, and then it's going to dump the material to the side of the cone. And now that the material has been dumped, the robot is able to reset itself and retrack for the pile again, and find the pile all over again, and move the pile completely from point A to point B. And that's about it. So thank you for joining us, and yeah, see you next time.